Thanks. I'll begin with a word of prayer. Dearly Father, we thank you for the Christmas season, which is upon us. We just pray that you'd be glorified in what we do this day, that we would enjoy the time that remains this semester, that we would spend meaningful time with friends, but also get good studying done that we need to get done for your glory, Lord. In your name I pray. Amen. All right. So I was trying to keep you guys busy. Let's see here. First of all, this gives me 2x plus y cubed. Show of hands, who got this? Okay, good. Sorry, I don't want to single people out. I won't do that again. Okay, so this is, what do we got here? 3xy squared. All right. All right, so this and that, they're just notation for what we already did, right? This is exactly f sub x. This is exactly f sub y. The x partial derivative of f, the y partial derivative of f. So those are precisely the same. Now, to get fxy, you can either differentiate the x1 with respect to y, or you can differentiate the y1 with respect to x. You should get the same thing. So let's see here. If we differentiate the y1 with respect to x, that seems easier. I'll get 3y squared, right? But you can easily see that if I was to take partial y of this, I'd also get 3y squared, right? So whether you do partial derivative with respect to x of this one, or you do partial derivative of y with respect to that one, either way we get to 3y squared. So how about xx? I get 2. Yy? 6xy. So I hope once you have time to work on this, it should click pretty quickly. Like it's really not that bad, I think. I mean, I hope. Okay, so over here, fx is what? Fx is partial x of e to the x plus e to the y quantity cubed. So what do I have to do here? I'm going to write out the steps in this case. I got to do the chain rule. The chain rule says I do 3 times e to the x plus e to the y quantity squared, because this is the cube function. That's my outside function, right? Then I have to multiply by e to the x. Somebody let the elephants out of the pen upstairs again. Let's see here. It happens. I used to study with a guy which I affectionately referred to as Somber Paul, to contrast him from Crazy Paul, of course, who was crazy. Somber Paul was a more serious fellow. And but he had this apartment, and he had these, well, I don't know if they were overweight or not. He said they were overweight. And upstairs neighbors, and his theory was that they had a toilet that was just not mounted on anything, and they like to take it and just move it around, like just, I don't have anything, but it's like, shunk, shunk. That was his theory. That's the only way he could interpret the noise. It could have been an old person in a walker, and Somber Paul was a monster. I don't know. I mean, that's possible. What a jerk, man, in retrospect. I think he would be actually very happy that you thought that. 3 e to the x, plus e to the y squared would be the answer to this one. Because this derivative, right, this whole thing just simplifies e to the x, because that is constant, so that just goes to 0 in the partial derivative with respect to x. Now, in contrast, fy, almost the same thing. Okay, so this time, the partial derivative with respect to y sends this thing to 0, because e to the x is a constant with respect to y partial derivative. X is held fixed in this differentiation, and then we just get 3 e to the y times e to the x plus e to the y quantity squared. You have a homework problem quite a bit like this, by the way. Maybe it's with a square instead of a cube or something, but. Now, question, here's an example I really want to do, but I don't think I'm allowed to. By the forces who just designated this course to have a trig lobotomy. Those same forces, I think, forbid me to talk about this. Have I talked about this? I can't remember. Did we ever differentiate like 2 to the x or 3 to the x? Well, here's how you do it. Y equals 2 to the x. We take the natural log. I mean, it is a reasonable question for you guys, actually, believe it or not. So that's what? That's x ln of 2, right? By property of the logarithm. So if I differentiate implicitly, what do I get? I get 1 over y dy dx is equal to the natural log of 2. And so this gives me dy dx is equal to the natural log of 2 times y, which is the natural log of 2 times 2 to the x. There's nothing especially special about 2, and you can equally well do this example for base a. So like generically speaking, the derivative with respect to x of a to the x is equal to the natural log of a times a to the x. That was probably part of the required canon of this course 20 years ago. And public education happened, so whatever. Now, natural log of e is what? One. I heard a 1, yes, is 1. So what happens? So d dx of, you're going to tell me, you're asking a question, what's happening here? I understand. See, so this is that's a special case. The derivative of e to the x just being e to the x, that happens because the natural log of e is 1. Otherwise, you get some kind of scale factor in there. Yes, sir? Oh, then I have to do the chain rule. So like if I have derivative with respect to x of like e to the x squared minus x, for example, then I would have to do e to the x squared minus x times d dx of x squared minus x, which would be e to the x squared minus x times 2x minus 1, for example. Yeah. Okay, now that I reminded you guys these, or introduced it to you, as may be the case, I can give you an example which sometimes confounds 131 students, even ones who've been paying their dues, doing their homework and stuff. This particular example does have the tendency of causing people some trouble. So which one of these is a power function? Which one of these is an exponential function? I mean, these are simultaneously power and exponential functions, right? So the point is here, the base is the variable, right? And the exponent is fixed. So with respect to x, this is a power function. It's x, it's like, the base is x. This is a fixed exponent. So this derivative is the one we know and love. This is y, x to the y minus 1, right? Now here, the base is constant. That's like the a derivative we just did. And then the y is the variable. See, an exponential function, the variable is in the exponent. See, a to the x is an exponential function. X is in the exponent. That's the exponential function. Power function has the variable in the base. Anyway, this is an exponential function with respect to y. So this is actually natural log of x times x to the y. All right, I think that's enough partial differentiation to get us started again here. So now that that's been accomplished, I want to give you a few examples of graphs of functions of several variables, which will help motivate our final topic. Okay? All right, so some examples. So the way this is going to work, I'll give us like maybe 4 examples, and then we're going to add something to these afterwards. So let me just try to draw myself some dividing lines. So the first example will be, z is equal to, let's say, 1 minus x squared minus y squared. So what this looks like, guys, is just basically like a mountain. And so here's the z-axis, and here's the x-axis, here's the y-axis. If you graph this thing, it looks like this. All right? And this z-intercept is 1. So this is actually what's known as a downward opening paraboloid. If you sliced it with any vertical plane, you get a parabola. I know it doesn't look like a parabola. That's the poor artistry on my part. Okay, so that's my first example. Now, what would you say about the top of the paraboloid? Is that a minimum? Is that a maximum? What is that? It's a maximum, right? We call this example 1. Example 2. And so this was, by the way, this was f of xy. So let's look, example 2, z is equal to f of xy. This time, we'll let f of xy be, how about the same thing with plus? Then it looks something like this. So it's an upward opening paraboloid. Can't spell paraboloid. Oh well. This time, the lower point here, this is what? Minimum, right? This was the maximum. Maximum z, right? The minimum z value taken on the graph. Third example. I'm not very good at drawing this one. But something like this, z is equal to f of xy is equal to xy. So this one's kind of funny. I won't be able to draw a very good picture of it. I'm just going to show you what happens. First of all, if you think about this, well, for the origin is on this graph, right? I mean, there is this point. If you put x and y as 0, you get z is equal to 0, right? What else is on the graph? How about x equals to 0? What is x? If x is equal to 0, z is equal to what? 0. If y is equal to 0, z is equal to what? So that means that the coordinate axes are contained in the graph. Like this is the coordinate, the x-axis and the y-axis, those are part of the graph. What happens if where x and y are positive? Product of two positive numbers is? And what about when x and y are negative? Right, so like it's going to like grow up here. It's going up, right? And likewise, here it's also growing up here, but I don't want to, okay, fine, I'll draw it. I can't draw it worth anything, but it's lifting up. So it's lifting up there and there. And then what happens where x is positive and y is negative, or vice versa? It's dropping down here, right? I don't know how to illustrate it. Maybe something like this. So the blue is below the xy plane. Maybe if you have a very good imagination, you can see that if you like turn this thing, it looks something like a saddle. But I think you have to have a very good imagination to see that in my picture. So like, it's hard for me to draw. The x-axis is something like this, and the y-axis is something like that. The point is, the origin here is neither a min nor max. This is a saddle point. So, a fourth example, I think last time also, something like z equals to f of xy equals to, say, x plus y quantity squared. This is going to look like a trough. So the origin would be something like here. And so this is, well, it's kind of a minimum, right? It's sort of a minimum. Technically, it depends on how we parse the definitions, but anyway, one direction has what? Z equals to f of xy constant. In fact, z is equal to 0 along what? Where's that trough? Where's the let me make it blue. This line in the xy plane, right? This is actually the line y equals to minus x with z equals to 0, right? So this graph is constant in those directions. These are some of the simplest graphs of functions of two variables, right? Is there some way we can understand what, first of all, is there some way we can find these points where we either have a local maximum or a local minimum or a saddle point or a point in which one direction is constant? Is there some simple algebraic thing we can do to find such points? The answer, thankfully, is yes. The place where there's an interesting point is known as a critical point or a stable point. So let me define that for you. And so if f of x comma y has fx at a comma b equals to 0 and fy at a comma b equals to 0, then then a comma b is a critical point of f. So one of our jobs then in this section is to find critical points. Let's find the critical points. for my examples. Let's see here. Number 1, we have f of xy equals to, what was it? 1 plus x squared, well, I'm sorry, 1 minus x squared minus y squared, right? So fx is what? Maybe I should do it. No, I won't. I better do it here. Fx is what? Fx is minus 2x. Fy is minus 2y. Set those equal to 0. We get that 0, 0 is the only critical point for this function. All right. Example 2. Almost the same thing, right? Example 3. We have what? F of xy equals to xy. This time fx is equal to what, and fy is equal to what? Finally, a little bit of variety here. Fx is what? Y, right? I mean, why not? How about fy? Is x. Yes. All right, so this is equal to 0, this is equal to 0. These equations are really easy to solve. Like, there it is. Okay, so 0, 0 is critical. How about example 4? We have what? We have f of x comma y equal to, and you know what I'm going to do? I'm going to multiply that out, right? That's x squared plus 2xy plus y squared if we distribute, right? Do you guys see that? What did I do? Algebra. Yes? Okay, so then what's fx? It might have even been smarter not to do that. I don't know. So that's 2x plus 2y, which is 2 times x plus y. Yeah, I shouldn't have multiplied it out. I'm dumb. Fy is 2x plus 2y, which is 2 times. I mean, if I hadn't multiplied it out, we would have gotten twice x plus y without algebra, right? You see what I'm saying? If I just differentiated this with using the chain rule, I would have immediately got 2 times x plus y for x and y respective. So by multiplying it out, differentiating, and then regrouping, I made myself work. It may or may not be the right strategy to do algebra, then differentiate, or vice versa in your homework. This is a freedom you have, right? You can manipulate expressions before or after you differentiate. Okay, just something to think about. It's a freedom that you have. Now, if these are equal to 0, what do we get? We have the solution, critical points, x comma minus x for any x. So my fourth example has infinitely many critical points, which is totally unsurprising from the graph, right? The whole trough, each point on the, at the bottom of the trough is the same. So if one's a critical point, they've all got to be critical points, right? Okay, so the fact that something's a critical point, is that enough to tell us that it's a minimum or maximum or a saddle? It is not. So it turns out from studying the thing we looked at last time that you can look at something called the Hessian, which is this thing called big D. Now big D is fxx, fyy, minus fxy squared. I would love to tell you more about the significance of this, but, well, I'll tell you a little bit. Basically, here's the thing. If d, so for a critical point, if d of a comma b is less than 0, then f of a comma b is, well, let's say the point, then a comma b is, to be more specific, a comma b comma f of a b, sorry, is a, stupid, saddle point. Number one. Number two, if d of a comma b is greater than 0, then a comma b comma f of a b is a, case 1, minimum if fxx at the point a comma b is greater than 0, and case 2, a maximum if the second partial derivative with respect to x at the critical point is less than 0. There's a case 3 overall that I can write here. I don't really have to write it, but I'll write it just for the sake of kind of, telling you how the story goes. If d of a comma b is equal to 0, then d is useless. So this altogether is our beloved second derivative test. Basically, the proof of this theorem basically reduces to the following comment. If the Hessian is negative, you can change coordinates so that it basically looks like this. In fact, this is the same as something that looks like x squared minus y squared in a different coordinate system, x bar squared minus y bar squared. You can actually rotate coordinates to make it have this formula. And so if the Hessian is negative, there's some system of coordinates where the graph looks like one coordinate squared minus another coordinate squared. If the Hessian is positive, then if fxx is negative, what is the d here? D is equal to what? What is fxx? Minus 2, right? What's fxy? 0, right? So this is equal to 4, which is greater than 0, and fxx is equal to minus 2, which is less than 0. As you can see, what'd I do? Oh, useless. I'm sorry. My writing of useless was useless. This feels like a good time to make a Justin Bieber joke. Oh, but he's reformed. What am I talking about? Would any of you like his movie? I happen to have a copy of it. Well, this ex-student of mine was moving out of her apartment, and her previous roommate, they're all international students, and they left, and they just left all of their stuff. So she's the last person to leave this apartment, and she had an inordinate amount of garbage. So one of them was like a Bieber fan, and what is his movie? That one. Yeah, I have that. If you'd like a copy. No? Okay. Yeah, no one's taking it from me. We hosted a Japanese student. When was it? The summer? I forget. And she was a big Justin Bieber fan, but of course she already had the movie, so she wouldn't take it. That's the closest I've come to getting rid of it. I'll get rid of it someday. Let's see here. So anyway, this is just evidence that the second derivative test makes sense. See? The d is positive, the second derivative is negative. That is a maximum. This one, d is equal to what? Again, fxx, fyy. This time it's what? It's 2 times 2 minus 0, which is equal to 4, which is greater than 0. And fxx at the point 0, 0. In fact, at any point, fxx is 2, right? But only at 0, 0 is it a critical point. Does it have significance there? That's greater than 0. So therefore, 0, 0, 1 is a local minimum. In fact, it's a global minimum, but that is above our pay grade in this course. This one, example 3, the Hessian. Again, fxx, fyy minus fxy squared. Man, if only you got like a page of notes for the final where you could just write this thing down and not have to memorize it. Oh yeah, you do. Okay, good. I mean, this is not something that I would encourage students to memorize anyway, unless they're a math major, and I would berate them for not knowing it. But let's see here. fxx is what? 0, 0. fxy is? One. You see, if I take two derivatives with respect to x or two derivatives with respect to y, I get 0 there, or that one. Do I need to write it out? You guys with me? Okay, judge that to be a yes. So this is equal to minus 1, which is less than 0. Game over, saddle point. At the origin by the second derivative test. And in case 4, what do we have? So you can pick any point. I'll pick 0, 0, 0 to study. You can pick any point on the trough, and the same story goes. The Hessian, what is fxx, fyy minus fxy? I mean, it's 0, it's 0, it's 0, the Hessian 0. No dice, no information. So, what do you guys think? Shall we try something harder from your homework? Sure. I think we should do that. The main point of difficulty, all right, well, that one's not hard. Well, that one's not hard. Man. I mean, I think problem 7 and problem 8, I think you can do those. I'm not going to do those in here. You can do 7 and 8. 7 and 8 are almost what I've already done. Problem 9 actually has a little bit of algebra in it, so I'll work problems 9, maybe 10 here, the time that remains. Let's see if we can do it. Can I erase these? Is that a no? I guess I don't need to. I can work over here. Homework 18, numero 9. So here we have f of xy equal to x squared minus y squared minus 6x plus 8y plus 2. And you're supposed to find critical points and use the second derivative to classify any critical points you find. So what's our first order of business? We calculate fx, and we calculate fy. What do we get? 2x, right? Minus 6. That's it for the x's, right? How about the y's? Minus 2y plus 8. Now I set these equal to 0. I'm sorry, did I say these were difficult? I think I was insulting your intelligence. So this says what? This says that 2x is equal to 6, which tells me x is equal to what? 3. Oh man, these aren't that hard. I gotta find some harder problems for you guys. It's very disappointing. So this says 8 is equal to 2y, I suppose, which tells me that 4 is equal to y. So altogether, we have the critical point, 3, 4. But I have to add it to the other side. Yeah. This is our sole critical point. All right. So now we calculate the Hessian, right? So what's fx? fxx, fyy, fxy, what are those equal to? Oh man, these are really boring. I'm sorry. 2 minus 2. This is very disappointing to me. 0. Ah, well, really? It's just no fun at all. D is fxx, fyy. I mean, you don't even have to plug in the point. Generally speaking, you have to find formulas here and then plug in the critical point. I can't even see that in these examples. But they're the ones I gave you, so I'm stuck with them. All right, so this is 2 times minus 2 minus 0, which is minus 4. Uh-oh, less than 0. Therefore, 3 comma 4 is a saddle point. And of course, there's an abusive language here. I mean, technically, I guess I should say really, what, 3 comma 4, f of 3, 4 is the saddle point technically, but I allow us this abusive language to not talk about the z component if you want to. I think they do the same, yeah. All right, I have some hope that the last homework problem at least has something more to offer us. Some adversity. I hope. I mean, come on. You know, next time I teach this course, I got to pick out some harder homeworks. I helped my wife write some of the tests for the online version of this, you know, and I put some pretty hard problems on her tests. Well, come on, they have open book tests. I mean, and they got like 2 hours to do it. It's a little different. Do. All right, so that's the question again is find critical points and classify them. All right? So we do the same thing again. We calculate the x derivative, calculate the y derivative, set them equal to 0, find the solutions or solution. So fx is equal to what? It's 2x plus 2y minus 6. All right? What's fy? Fy is equal to 2x plus 4y plus 10 Yay, there's something to do. Okay, so 2x plus 2y is equal to 6. So if I set this equal to 0, I have to solve the system of equations. 2x plus 4y is equal to minus 10, right? Two equations, two unknowns. Does this make you nostalgic for middle school? High school? College? I don't know. Different strokes for different folks, I suppose. Let's see here. So you just subtract the equations. That's what I would do. That would give me minus 2y is equal to minus 16. Therefore, y is equal to minus 16 over minus 2, also known as 8. Did you know you can subtract equations? Oh, man. Thank you. Wait. Oh, yeah, positive 16. Thank you. You guys are way ahead of me. So 16. Oh, so it's minus 8. Thank you. And then how do I find x? Yeah, just plug it back in, whichever one you want. So 2x plus 2 times minus 8 is equal to 6. So 2x is equal to 6 plus 16, which is 22, which tells me that x is equal to 11. So altogether, my critical point is 11 comma minus 8. My sole critical point. Now what do I need to do? I need to classify the critical point. Is it at a saddle? Is it a min? Is it a max? What's its deal? You said min? Or was that just a... Let's see here. So so I'll calculate my second derivatives. fxx is 2. fyy is 4. fxy is 2. So this gives me d is equal to 2 times 2 minus 2 squared. What? Oh, I'm sorry, I can't do math. 4. This is why I should write it down. fxx, fyy minus fxy squared. Okay, so what are those? 2 times 4 minus 2 squared, which is otherwise known as 4, which is greater than 0, right? Observe d is greater than 0, and fxx at the point 11 comma minus 8 is equal to the same thing it's equal to everywhere, which is 2, which is greater than 0. Therefore, 11 minus 8 is a what? Minimum. Very good. Yep. This is the end. Would you guys be terribly offended if we didn't have class Tuesday? You want me to have class Tuesday? Oh man, you guys still have questions, don't you? Fine, we'll have class Tuesday. I will be here to answer your questions Tuesday, but that's it for the material. So, yeah, don't clap for that. Let's clap for something worthwhile. Have you guys seen this? Never. Oh well. Whoop. Uh-oh. Gotta be careful pulling this out. If you pull it out wrong, you turn the whole thing off. I really needed to use the projector Tuesday, I think, and I pulled this out the wrong way, and I somehow unplugged the internal unit, which is locked behind a door, by the way. It was awful. It was the hardest thing I had to prove all semester. I had to do it all by hand without projecting. It was. You guys can't really appreciate it in here. Like I said, I need to give harder problems in here. But in Calc 3, there's some difficult things. Whoop, whoop. You've already seen it. Why would I make my way? What is going on here? Why can't I hear anything? Whoa.
You're the guy that made this ghost, right? Yeah.
That's theology. What made this really fun for me is like my wife has come across this somehow on the Facebook, you know. And whoa. Oh, what? Oh, the sound is kind of. Anyway, my great joy in this was like my wife liked this just because of the content of the song. She's completely unaware of the Adele song. So like driving in the car, I've got the radio on to like the top 40 station or whatever, and she'll be like, "It's that song." I'm like, "Yes." Well, anyway, you've been forced to watch this already, so I won't force you to watch it again. No, okay, I'm sorry. I think my internet connection here is questionable.